It is a pleasure for me to open this session of our seminar, the more so that one of our colleagues, Andrzej Bojar, will give us his talk. Just as one note before you start talking, because I have a question actually. I don't know who of you watched the TV some days ago, where our colleague, Professor Barták, answered some questions concerning artificial intelligence and the influence of artificial intelligence on different branches of science. And I don't know whether it was his quotation or whether the interviewing person had this slide prepared before the discussion, but the slide concerned answer of one question. When the artificial intelligence will help or will make it possible for a system, or for which systems it will make it possible to surpass the ability of a human. Or in other words, when the AI system, in which branch, will be better than a human system, than people. And there was a scale of years. The first on the scale, you can imagine, was automobile industry with automatically driven cars. And the second on the scale was machine translation. And the date there was 2024. So my question is, do you think that in 2024 the AI or deep system will be better than a human?
Yeah.
That's your turn.
Yeah, thank you for the interaction. So to give you a short answer, I thought that the slide would say yesterday, but not quite, obviously. Welcome to the talk on machine translation. It's called Deep Turnaround. So I'll be talking partly about machine translation, but I'll depart from that later on. Here is a quick summary. I have too many slides prepared, so maybe let's skip the summary and let's start. Let's start with the. Let's skip the overview and let's start with the nice messages. It's always good to start a talk with something where you can show off and tell your success. So this is the success that we had in the past. In 2013, there is a machine translation competition in our system that combines all the systems developed at this department. Deep syntactic, phrase-based, and also automatic error correction systems. Altogether, these systems were able to perform best in English to Czech translation, and they beat it the Google Translate, which is always hidden as online B in these rankings. So the same success happened next year. In 2014, we actually did more variations, so there are more kind of winners of all us. And in 2015, we were also happy because we were still the best performing team in this particular language direction. And I highlighted this blue line that nobody really noticed. That was the neural MT system competing in that task that year. And we didn't care about that because, well, it was on the third place. So we just thought that we were doing the best. So in 2016, something horrible happened. We still improved our system as we did every year, like adding more data, clean up, retrain models. We tried many new ideas. Some of these ideas don't help. Some of these ideas do help. That's common. So you select those that work and you employ them in the system, and then you go for the competition. And suddenly we were the fourth. So that was annoying. And the two top performing systems were Neural MT, one run by colleagues from Edinburgh, and the second one was these people from, well, we didn't know them before at all. They are from machine learning in general, and they probably started with vision first. I don't know what their full history was, but so they attacked the goal of machine translation without knowing anything about language, anything about machine translation. They only tried to do sequence-to-sequence modeling task. It's not surprising that it was the Edinburgh people who won, because these people not only learned the new thing about how to do neural empty, but they also knew something about machine translation. So they knew how to use data and what is important in the data. So we sat together and we said, well, let's focus, let's do many things. Let's try Chimera, which was the name of our system, with neural empty in the back somewhere in the behind the scenes. So colleagues of mine who are not here at the department were also obviously very interested in this. So they developed and they still develop their own toolkit. It's called NeuralMonkey, and it's very flexible. So you can try various model parts. You can combine the neural empty model, and you can experiment with that. NMT was known when we were trying that for needing many days or even weeks of training. So in order to train the systems faster, we actually organized a shared task where the system was given. It was a NeuralMonkey system, and all the participants were supposed to help us with the speed up of the training, so that we would get a stable trained system in less than 3 weeks. And then for our particle submission, we tried many things. I'm not going into all these details. So these are various ideas how to train better so that the performance would improve. So here is a summary of what helped. So, well, NeuralMonkey is there, and it's a nice toolkit if you are interested in starting with that, and if you are interested in like plugging, playing as with Lego blocks with the neural empty systems. Then the NMT training task, yes, that was a little competition on its own, so that was carried out as well with some success. And we actually won in this particular task, so that's where our success was this year. But all the various variations of the architecture or training criteria or the various meta parameters that we explored, they didn't bring any significant improvement. The only thing that really helped us, that was known before, was to subsample for the right test set. So to focus, do some domain adaptation so that the neural empty is trained to translate text of that particular kind, which is news in this case. Okay, so with all this experience, all those like dead-end roads, we said, well, let's do our best. We simply use our previous best system, which is the Chimera phrase-based system combination. So we will just add the neural empty to that combination as one more system. In short, the system that we were submitting to this year's competition was a phrase-based, and I'll briefly tell you how that works in a second, was a phrase-based machine translation with several phrase tables. The standard one is based on large data set. This year we used only synthetic data set, which might be of interest for some of you who are doing machine translation. We include the outputs of the deep syntactic system, which was always the main gain in the previous years. So that was the difference that we had compared to Google Translate, for example. And this year we also added some neural empty outputs, because we knew that these are very good at producing fluent sequences of words. So we wanted our system to have that capability. And then, as always, we corrected it with the grammar correction and especially negation recovery system depth fix. So here's the result. And as you see, we are still like it depends how you count it, but we're on the third or the sixth position. And it's the neural systems that win. So obviously, last year in 2016, not only us but also Google got annoyed. So Google have thrown their engineers on that, and somehow they were more successful than we were. So Google NMT was better than everybody else except Edinburgh. So Edinburgh is the place to go if you want to do machine translation in the modern style. Okay. Actually, we were quite optimistic before submitting that system because based on the automatic measure BLES score, we got a silver medal. So this is the Edinburgh system, the winning one, and there is a big gap between the best one and our result, but still our result was like the second highest score in the automatic scoring. So you see that the automatic measure that breaks the sentence into short pieces of up to 4 words highly overvalues our translation quality. So the Edinburgh system is good in both short chunks and also the whole sentences. Our system is very good in the short chunks, but it's totally bad in overall sentence correctness or overall sentence grammaticality. So that's the annoying thing. We were hoping to be second, and we were like before. So is neural MT that much better indeed? So there are a number of Czech speakers. So for those who can speak Czech, please guess which of the outputs is neural MT, and this is the best system from this year's competition, which is the Edinburgh neural MT system. So which one is machine translation and which one is the reference? So it should be fairly easy here. So found dead. So the machine translation got obviously terribly confused by the capitalized title, and it didn't translate many of the words. So here's another sentence. A 20-year-old chef who had recently moved to San Francisco was found dead in the stairwell of a local mall this week. And then 28letý kuchař, který se nedávno přestěhoval do San Francisca, byl tento týden nalezen mrtvý na schodišti místního obchodního centra. Nebo 28letý šéfkuchař, který se nedávno přestěhoval do San Francisca, byl tento týden v schodech místního obchodního domu. So I guess that you would say that this is machine translation. Well, it's the reference. So the humans have forgotten the verb, and the neural MT was perfect in the whole sentence structure, including the subordinate clause and including all the agreements within the noun phrase. So another example. Mluvčí společnosti Sons & Daughters uvedla, že jsou jeho smrtí šokování a zdrcení, nebo řekl, že jsou jeho smrtí šokování a zničení. So which is the MT? Well, you would need to know the gender of the spokesperson in order to correct this. So in this particular case, the MT was this one, and zdrcení actually sounds to me better than zničení in the reference. So again, I kind of like the machine translation better than humans. Another example, here the difference is that Louis Gali Shah is either, there is a typo in the person's name, and either the typo was done by the people or by the neural MT system. So again, you can guess, in this case, it was the MT that made the little error. But otherwise, all the outputs are perfect. Another example, the police arrested 2 men So the question is whether arresting should be translated as obvinila or zatkla. And I've disclosed who is what, but honestly, I do not know in what context the verb to arrest can be translated as zatknout, and in which context it can be translated as obvinit. I believe that one would have to know the legislation and the legal procedures, and it can also differ from country to country. So I just wouldn't know how to pick the right translation. Oh, yeah. That's kind of suspicious. Yes. So there is an extra information, and we know that, well, at least this year, the neural MT systems still have not accessed the context of the previous sentence. I believe that the next year, many of the systems will access the context of the previous sentence, and it is therefore possible that even the neural MT will insert some facts from the previous sentence. So that's, yeah. So there were creative differences on the set and a disagreement. Došlo ke vzniku kreativních rozdílů na scéně a k neschodám. Na place byly tvůrčí rozdíly a neschody. So what would you guess? Which is the reference and which is the MT? Well, the MT is better. I'm sorry. Yeah. Okay, so last example. Economist Secretary Keith Brown visited the site. Ekonomický tajemník Keith Brown stavbu dnes navštívil a byl mezi prvními, kteří přišli z pevniny na most. Ministr hospodářství Keith Brown dnes místo navštívil a byl mezi prvními, kteří vyšli ze země na most. You would have to know the position, the name of the position, and its translation of Keith Brown. It's a Scottish, and I guess it's indeed Minister hospodářství, but I'm not sure if the translation. This is like the general translation that appears everywhere on the internet. Actually, the training data covers the internet better than the human translator did, because I like this translation better, and it's the machine translation output. So here is my summary of just a handful of sentences. It's like 1/10 of the sentences. Me and some of my students have blindly annotated it, guessing which of the outputs is neural empty and which of the outputs is the reference. And obviously there is some disagreement in the annotations, and not everybody did all of the sentences. But in general, looking at the empty output, at the real empty output, myself, I was able to tell that this is the empty output in 76% of cases. I didn't know in about 20% of cases these two outputs were so close or so incomparable to me, and I was thinking that this is a human translation in almost 5% of cases. So on average, about 10 to 20% of outputs are not really distinguishable from humans. While doing this annotation, I also, myself and the students, we were also like labeling the outputs, and we were saying whether they are flawless or almost flawless. And almost flawless is like that one click and edit of a word should fix it. And the summary of this little annotation is that 30 to 50% of outputs seems flawless or almost flawless. Yeah, okay. So that's the clear result from this year. So the neural empty is totally chasing the statistical machine translation. You will see the details how this works in a second. There are still some catastrophic errors. So these are the outputs from the same best performing system. So said Frank initially stayed in hostels. The hostels were suddenly translated as Budějovice. Then most of the Clintons' income, většina příjmů kliniky, so the Clintons disappeared and some clinic appeared. The 63-year-old 63letý mladík se nyní stal zvláštním zástupcem. And he listened to the moving stories, naslouchal pohyblivým příběhům žen. So I think that some of these, well, these are like stupid errors, but I guess that this type of error is almost the human-like. Like if you did not know, and if you were forced to translate, and you were too lazy to look up in the dictionary, then you might be tempted to produce such a translation. And I don't have more examples of this kind, but I think that the neural empty is slowly making errors similar to humans are making, and that's nice. That's a horrible one. So the reference is Thomas Gibson, hvězda seriálu Myšlenky zločince, byl propuštěn poté, co uhodil režiséra. And the translation is: kriminalisté Minsku hvězdu Tomáše Gibsona vyhostili po zásahu producenta. So that's a totally fluent sentence. It just says something different. And this is also a horrible thing. Přidejte k tomu svou dlouholetou nenávist, přidejte k tomu svou dlouholetou záštitu. So I had to look up this error, like how come that grudge was translated as záštita instead of nenávist. Well, grudge is zášť, and the neural empty is doing some segmentation of words. I'm not covering these details. And zášť is a rare word, so it's easy for the neural empty to like make the output string fluent by continuing this unknown zášť with záštita. Okay. Well, these are examples of German to Czech translation, and we can compare the statistical machine translation, the phrase-based empty, with neural empty. I'll again, because it's translation in Czech, I'll just I'll just read the Czech output. So the reference is: je to jako pěvecká soutěž Eurovision. The SMT says: podívanou připomíná hudební soutěž Eurovize. Which is a clear role reversal error. Divadlo se podobá Eurovizi Conview. Divadlo se podobá Eurovizi, that's fine, but Conview is something that never appeared in the input, so that's like a made-up word. Globální oteplení nebo kolize s zabijáckým asteroidem, that's the reference. Globální oteplování nebo srážka s killer asteroids, that's the output of an SMT system. Globální oteplování nebo střet s zabijákem. So here the NMT is more fluent, but it's like removing the asteroid, so no one would really understand it. Příliš mnoho zraněných pocity, that's typical of statistical machine translation. Even the very local coherence, grammatical coherence is wrong. The NMT said příliš mnoho zraněných, which is more fluent, but it's not exactly the same meaning. Okay, so what went wrong in our setup this year when we still use the phrase-based MT backbone and also with the other setups? So as a reminder, statistical, like the classical statistical which is big, because neural MT is also statistical. So I have to distinguish statistical and neural by saying that when saying SMT, I mean the classical, the non-neural machine translation. So the non-neural machine translation aims to produce a target language sentence which is maximizing the probability, this conditional probability among all the possible translations given the source string. And there is little statistics done immediately on this formula. So you can decompose this single probability table into two separate modules. One of the modules is called the translation module that checks the translation equivalence of the source and target, perhaps reversing it. And the other one is the language module, which checks the fluency of the output. In short and pictures, we have the input, Peter left for home, and we break this input into phrases, and that's the phrase-based MT approach. Other decompositions could be done as well with, for example, syntax-based systems, but phrase-based MT on general performs better. So we break it into these phrases, and then for each of the phrases, we have possible phrase translations. So these phrase translations, this is one of the possible phrase translations. So Peter alone could be translated as Peter, left for alone could be translated as odešel, and home full stop could be translated as domů full stop. So these are like three puzzle pieces, and the translation module is what brings these puzzle pieces in. It brings them in with some scores that will be later used to find the best of the possible candidates. And these puzzle pieces are put next to each other, and it's only the language module that has like overlapping pieces. So these are the dashed pieces, and that checks the fluency, the overall fluency of the output, like bridging over the puzzle pieces. And the language module also brings in some score. And then these scores are weighted, and the weights are trained. So after applying the weights, you will see that this particular candidate translation has this score, and you compare it with another candidate translation that has different pieces, different order of those pieces. So you select the best, the highest scoring translation. Here's an example of the process. So you start with some training data. That's sentences that were previously translated by humans. You align them by words. You extract phrases. So that's the puzzle pieces. And then some new input comes, nemám kočku, which means I don't have a cat. And you use the puzzle pieces that you have seen in the training data. So you translate nemám as I have and kočku as a cat, and that's it. So that's the crucial error which statistical phrase-based MT is bound to make. It translates piece by piece, and it easily forgets other links in the sentence. And in this case, the positive output, I have a cat, is even more likely than the negative output. So the language model, which checks the output only, will be happy about this, and it will promote this translation. So the core problem is that there is too strong phrase independence assumption. You are breaking the output, the input into pieces, and you assume that each of these pieces can be translated independently of the rest, which is not true. And the language model, which is the only tying element in that, is a separate unit. So it just checks whether the output sentence is nice on its own. So it doesn't check the source links at all. Yeah. So what NMT does, what neural MT does, it totally redefines the probability. It says, let's model the condition probability of the target candidate given the source sentence directly. So let's produce the target sentence word by word. So the target sentence is nothing but a sequence of target words in their order, and we are conditioning on the source sentence. This is like a joint probability, and we can decompose it into a sequence of conditioned probabilities. So that's the essence. We are predicting the next word given the words that we have already produced, and we are also conditioning on the whole source sentence, a sequence of the source words. This is very similar to the language model, if you are familiar with that. So you can say, if you want to like dishonest the null empty, you can say, well, this is just a clever language model. It is a language model that fabulates sentences, produces them word by word, and it conditions on the source. So that's the only difference. And indeed, that's it. So now the question is, what technical device can learn this? Because this is a very complex probability table. You have many possible words here, and you have many possible source sentences, and you need to condition on this complex space to predict the next word. So that's it. Neural networks are able to do this type of learning. So to start with, who has attended the class on deep learning by Milan Straka given here last year? Okay, that's too few. So remember, this summer the class runs again. So you should you should definitely go there. I'm going only to very quickly skim over the ideas, but it's. From what I've heard from other colleagues as well, it turns out that deep learning is going to be everywhere. Like companies, starting obviously with Google, but also other companies, are simply replacing all their software pieces, software modules, with trained systems. So I'm afraid that the classical programming will not appear in production anymore. Like all the systems that you see on the web, for example, in Google, in the search, if you type something, sometimes you get direct recommendation, sometimes you have you get like direct answers. All these modules are like launched and selected again by a trained system. So it's all trained to give the best performance. And other, even in smaller companies, colleagues said that they are kind of sorry. They want to like use their knowledge and write the rules because they know how things should behave. So they write the rules and they debug it, and then someone just hacks the few lines of the neural network setup and trains it with the data, and the neural network performs better than those rules. So yes, but please start learning. I've started just a year ago, which is too late, and I would need another master degree to understand enough. But anyway, so neural networks are universal approximators, so they can learn to approximate any function. That's there's a theorem that proves this. You can have just one hidden layer, and it will be able to learn this if the hidden layer can grow. If you can have many neurons here. So to give you some understanding of what the neurons are learning, this is an example from Playground TensorFlow.org. If you are bored, please raise your hand so that I jump over. But if you are not bored, then I'll go through this. So here the exercise is to classify points in the center and points in the circumference of a circle. So the network is trained with these training data. These are the dots. These are the training data. The network is trained to distinguish centrally located nodes and the outer boundary of that. And the network, as its inputs, gets two parameters. So it's just two coordinates, the x coordinate and the y coordinate of each of the nodes. And the network has three neurons in the hidden layer, and then one neuron that like classifies it. Let me start with a setup where the network would not need any hidden neurons at all. So if we modify the input and if we feed in coordinates as x squared and y squared, then as if you remember the formula for circle, which is x squared plus y squared equals 1, then all the computation that the network has to do is to check whether x squared plus y squared, so these two input features, are smaller or higher than 1. And based on this smaller or higher than 1, it can distinguish. So if the input features, if the input coordinates are perfect, there's no need to modify them at all. If we go back and if we say we are feeding in the x coordinate and the y coordinate, the network has to somehow calculate whether we are in the center or not from these two coordinates. So what all the neurons do in the hidden network is they only take some weighted combination. So each of the neurons takes a weighted combination of the input coordinates. The weights are the trained thing, and then it has a nonlinearity, a function that is applied on this weighted sum. And if the value is above something, then it would fire, and if it's below something, then it would not fire. If the activation function was like a thresholding one. In fact, the one that is used is not a thresholding one; it's a smooth thing. But the essence is that it fires if the weighted inputs are above a threshold, and it doesn't fire if they are below a threshold. So in this case, we have given the network 3 neurons. We have simply told that we want the hidden layer of the size 3. So it has, each of those has 2 weights, and each of the weights multiplies the x coordinate and the y coordinate. And the weights differ in each of those neurons. So as you know, a linear combination, like a weighted sum of x and y coordinates, a linear combination renders a linear line in the 2D space. So each of the neurons has the capacity to learn like a linear boundary. And these 3 neurons then used in the next layer together can combine these 3 linear boundaries to draw a triangle. So then we add up the outcomes of all those 3, and if the addition of those 3 is above, 3 or depending on the normalization or 1, then we will say, well, this is above all it's like on the right side, on the correct side of all the 3 border lines, and therefore it is in the middle. So the hidden layer is learning some modified representation of the original input. Each of those neurons is learning that independently of the rest, so that they jointly work best to classify that. And there is the last thing that also learns how to combine these 3 and how to produce the output. So we have seen that with perfect inputs there is no need to modify that. If we do not give the network the capacity to learn like 3 lines, if we do not give it the capacity to learn any line at all, we are bound to like fail on this task. There is no way to linearly separate the middle from the border. And if we make the network overly complicated, it in principle has the capacity to learn even better better features, clever understanding of the input. But it's impossible to train it with the limited training data we have. So there is like a trade-off between the complexity of the network that you can afford for computational reasons, because this is many more numbers to try out, and also for data reasons, because you do not have enough evidence to reliably estimate the parameters. So neural networks have first caused the disruption in vision. And in vision, it's indeed the very same setup that I've shown on the previous slides. So it's like a sequence of layers, and each of those layers is converting the coordinates of the previous layer to identify some interesting features. And if the neuron sees a feature, it will like fire for the next layer, and the next layer combines those features. So you know already that if you are just combining the coordinates, you are getting various linear elements. So you're learning lines, which lines are important. then you know that if you combine several linear segments, you can find approximations of circles, so you can find like shapes. And then if you combine these shapes, even at like a higher level feature representation, you will learn little sub-objects. So the goal here is to identify that this is a car. And on the training data, the network has established that it is important to count round objects. It is important to count, well, like window-like objects. In the deepest layer, it is important to count, well, torches or birds. And then the classifier is again one more layer, and that says, well, I've seen four wheels and one bird. I think the bird is here, so it's a car. And that's it. That's how it works with vision. Okay, so here's one more way to look at it. It's called representation learning. So we saw that the deep learning is finding useful features. The useful features were like the boundaries, the linear lines that we use then to combine, or in the previous slide it was those circular and window-like elements. We can think of these features as new coordinates. So instead of talking about x and y coordinates of something, we will say how many wheels are there and how many windows are there. And then these new features, these new coordinates, are better to predict what we are training to predict. So in short, neural networks are learning to represent the input so that it makes it linearly separable for the particular task. The task can be object recognition. In neural empty, the task will be predicting the next word. Yeah. So here is a summary. There's just one formula. What one layer does. What one layer in neural network takes the input vector of coordinates, the x. It has the weight matrix that applies the weighted average to those. It has some bias which like shifts the values, and it has the nonlinearity, which could be, for example, the 10H function. So when we look at this from the representation learning perspective, we start with the original coordinates, the x and y coordinates. Then the matrix causes the skew, the distortion of those coordinates. So this is the distortion. Then the transposition causes a shift. So it's hard to see in this, but it's kind of a little moving to one direction. So that's the shift. And then the nonlinearity takes the whole space, the infinite to infinite, and it squashes it so that it fits into the rectangle 1 to 1. So that's like the representation learning. The original representation was x and y coordinates, and the new representation is this skewed, distorted space. And these like techniques or modifications of the coordinate system are then used by the classifier so that the classifier learns to distinguish the elements it has to distinguish. So here we have the classification task similar to the one that we had before, like finding the center versus the circumference of a circle. Now the two classes are these two parts of the spiral, and the network with 4 layers is trying to change the representation, to change the coordinates, so that these two, the red points and the blue points, are linearly separable. And you see in the animation that it like first squashes it, then it folds it, and then it like pulls it apart. And here you already see that there is some chance to draw a straight line. Finally, when the training is finished, indeed, you draw a straight line, and everything that appears above the straight line belongs to the red part of the spiral, and then everything what is below belongs to the blue part of the spiral. So that's what the networks are doing. They are modifying and trying all the various combinations of those weighted of those weights, the weighted averages, so that the space gets distorted in a horrible way, but making it linearly separable to distinguish the classes. And it's the computing power behind that, all the many numbers that can be tried in a second, that allows the system to actually find these settings. Okay, so now finally some words, because we're doing machine translation after all. So if we want to process text with neural networks, one natural way would be to just list all the words we know, the vocabulary, as the length of as the labels of vector elements, and then every word in the sentence would be represented by this vector. This vector would be as long as the number of words in our vocabulary, and all the elements would be 0, and only one of those elements would be 1, and it would indicate this is the word that we're looking at. So if we have the input sentence, the cat is on the mat, the first word is the, so it will be all zeros for all the elements, for all the positions in the vector that are not the, and it will be 1 for the. Similarly for the cat, and all like that. So the only problem, this is like a good representation, but there is a problem with that. The problem is that the vocabulary size is easily 1.5 or 2 millions of word forms, and it can be actually much more. So we would have to have like a matrix. For example, if you want to represent the whole sentence, we would have to have a matrix that is tall 2 million rows, and it is as wide as the sentence length. And that's not practical. And there is another important problem. The important problem is that all the words are like on their own axis. So there is no relation, no like measurable relation between those. Either they are identical, they are the same word, or they are totally on a different axis, so they are unrelated. So that's the main problem, because the system cannot generalize for unseen words or for other contexts. So what people do is they map each word to a dense vector. So instead of those 1 or 2 million elements, they will say, we will use just 300 or 2,000 dimensions to describe a word. The dimensions, I have to highlight that these have no clear interpretation on their own. It could be things like, is this how much verbish or nounish the word is? It could be like how dark color does the word express? How much elephantiness does the word show? So these could be the dimensions. The dimensions are identified automatically and empirically to best help in these subsequent tasks. So one of the famous tasks is the task behind the word-to-vec training. Here the task, there are two variations of this model. One is called SIBO, continuous bag of words, and the goal here is to predict the word from its 4 neighbors. So this is like a language modeling task. So you take all the text in your language model or your corpus, and you always take 5 words, and you take the middle out, and you look at the outputs. You look at these 4 surrounding ones, and you try to train the network so that it embeds these, and it then is able to predict the word that was in the middle. So that's predicting the word from its neighbors. And some embeddings will arise from that. The other variant is the skip-ram model. It's predicting the neighbors given the word. This is the highlight. This is the zoom of one of those. So when predicting the neighbor, you have the one-hot representation of the input word. So this is all the ones and zeros. This is the weight matrix, which is actually the embeddings matrix. This is the hidden representation. So that captures how much that captures the word in the second layer, like in the hidden layer. So that's the hidden representation of the word. And from the hidden representation, the network is predicting one of the neighbors. So it's like a compression mechanism. So you have this sparse vector, very sparse, very long vector, and you learn the weights so that you like combine the indicators across the whole corpus to give you a compact representation, much shorter, the embedding of the word. And the embedding has to be designed so that it helps you best to predict the neighbors. you just have to live with that. So it's reading these reading papers about this a few times is the only thing that helps. It's like with mathematical analysis. You have to live with that for a year or two, and then suddenly you start believing that as well. Okay, so the interesting thing about this dense representation of words was also pointed out by Tomáš Mikolov. There are some like relations apparent in this space. So if you take the embedding of the word king and you subtract the embedding of the word man and you add the embedding of the word woman, then you arrive in the high dimensional space, in the 300 or 2000 dimensional space. You arrive close to the location of the embedding of the word queen. So there is some like linear relations. So this is illustrated here. If you like imagine the 300 dimensions scaled down to just 3 dimensions and then drawn on this board, there is this linear like shift operation that corresponds to the man-woman, to the gender relation between the embeddings. And similarly, there is another direction in which you can move in the embedding space to get from the present tense to the past tense of the word. And there is also another direction in which you can move to get from the name of the country to the name of its capital. So there are various aspects that can be examined in that space. Okay, so we have handled words. Now we need to handle sentences. So for sentences, sentences are of variable length. So one way to do that is to design the network so that it consumes the word one at a time, using like the same matrix that reads that consumes the word. This is called recurrent neural networks, and you then run it, and you will see more examples of that later on. You then run it over the input sentence, and it will produce a fixed size vector that somehow captures everything what has been read in the sentence. Essentially, you just unroll this in time. So instead of like running the network step by step, you put the calculations next to each other directly. Well, without formulas is difficult, and I didn't want to put formulas here. So what people do is they say a fixed limit on the sentence length, and then fill the unnecessary positions with just zeros, and then they have the matrix multiplications along this whole wide sentence, and then train the network to consume the whole input sentence to do whatever task is needed, such as if it was just sentence classification, then you would feed in the whole sentence, and the labels that you are attaching could be like stars for positive or negative sentiment in that sentence, or other or any other task. There are some tricks that I definitely do not want to talk about that are necessary to so that the training actually finishes at some point, and the training is stable. Yeah. So let's skip that, and let's look at that setup in other pictures. So it was Kyung-Kun Cho and other colleagues who first used this encoder-decoder architecture, which is 2 recurrent neural networks attached to each other as with a single connecting point, to estimate the probability of phrasal translation. So if you remember here at the very beginning, it's better to go there. Here at the very beginning we said we have phrases. So these are the variable length phrases. This is phrase of length 1. This is phrase of length 2 to 1. This is phrase of length 2 to 2. So these variable length phrases have their scores. And these scores come from a corpus, usually from like co-observation counts or co-occurrence counts. And now what the first encoder-decoder architecture was used for, it was used to produce one more score based on what the network has learned, using the word embeddings and some combination of reading the phrase one word at a time. So, that's this. So you feed in the input phrase one word at a time. Here, every of the nodes here indicates that the state that you receive. So there is like an input state which is zeros. You start with the first word and you just multiply each of those with a matrix full of numbers, and you add these two vectors together. You apply the nonlinearity, and that gives you the new state. And again, you have a new state. This is the recurrent network unit. You feed in the next word, multiply each of those with the respective weight that is there, add those vectors up, and then apply the nonlinearity, and so on. And the last state, which is just a vector of some numbers, encodes everything what you have seen so far, and this is the fixed length representation of the variable length input sentence. So you have mapped a string of words into a single vector of numbers. And I've told you, it sounds that as if I haven't told you anything, but I've told you the whole of it. Indeed, it just multiplies the numbers by other numbers, and these inner numbers are those that are trained so that it best does its task. So there's nothing but multiplication of numbers, doing weighted sums, and applying nonlinearities. And the weights is what is trained and what is all the cleverness in the system. So here we arrive at a representation, a deep representation of a sequence of words, and here they write it the other way around. Surprisingly, you enroll it. You like check the contribution of you can think of it as if you are producing also the output sentence, the target side of the phrase, word by word, and you predict what is the best word to produce now, given the compact representation of the source phrase and the word that you have produced already. We will see that in a second once more. So this helped. So this scoring, the neural network produced scores that were then useful for the phrase-based MT and delivered better translations. Before looking into this again, let me show you the examples from that paper where the hidden representation of variable length phrases, which is again a 300-dimensional vector, are depicted in a 2D space. So these are all the phrases that are considered by the system. I think it's they're only their source side, and we'll zoom into the violet and the blue area. So in the blue area, it's area where the phrases somehow show the syntactic pattern in that. So the phrases that arrived in the downscaling to the 2D that arrived in this area always are the something of the exit of the, with the approval of the. So these are the chief of the. So these are phrases that are similar. They arrived in the similar position in the embedding space because of their syntactic properties. Here is the zoom. Well, it's not important. This is another area. This is the violet area, and here are phrases that became similar because they are like semantically similar. So they represent some country names. Yeah. Okay. So that was the first sequence to sequence applied, and then is it that light? and then Ilya Satskever and other colleagues later on were able to scale it up to the full neural empty system that takes the whole sentence as the input and produces the whole sentence as the output. And they totally got rid of the independence assumption of phrases. So this is a summary of what we have seen so far. We have input sentence. Economic growth has slowed down in recent years. This is the one-hot representation, so it's all zeros except for the ones for the word that you are looking at the current point. you multiply it with the matrix of embeddings, so you get a compact representation. This is a shorter vector, and this compact representation of all the words is then used as the input of the RNN of the encoder. So there is again some matrix multiplication going on. You have some starting state, and you combine that starting state with the like deep representation of the word, and that gives you a new hidden state. And you consume all the input sentence, and the last state that you are at is the representation of the whole sentence. Then you unfold that, so you have the decoder, and the decoder is something that takes the compact representation of the sentence. It predicts what would be the best word to start with, and you emit the word, and then which could be la in this case, and then you feed in the word to the network again, so that it knows what it had just produced, and it will produce the next word. And you keep asking, and at some point it will suddenly say full stop, and that's where you say this is the end of the sentence and this is the translation. So this is the whole architecture. It's just multiplication of some numbers, and it's trained for 3 weeks, and then it delivers the translations that you saw. The space of the sentences is interesting. So this is a 2D space, 2D projection of an 8,000 dimensional space of sentence embeddings, and you see that it clearly distinguishes who are the actors and patients in the event. So closer to each other are sentences: in the garden I gave her a card, she was given a card by me in the garden, I gave her a card in the garden. And further away are sentences: I was given a card by her in the garden she gave me a card, she gave me a card in the garden. So the closer representations are those that are more semantically closer. Okay, so let's actually skip, let's skip this for the sake of time. So what improved the translation a lot was adding the attention, so that the network for machine translation has the capacity to return to any of the input words during producing the target, and therefore it is not forced to encode the whole meaning of the sentence in the vector. But it's not too relevant. It's very important for the quality of machine translation, but it's not too relevant for the rest of the talk. So I'll skip that. The big change that happened when we moved from the classical statistical machine translation to neural MT is that in the classical SMT we were trying to find minimum translation units, which could be graph partitions or subphrases in a sentence, so that they are frequent across many sentence pairs, and they are not too wildly reordered, and they can be learned in an unsupervised fashion. And then we would break the input into these minimum translation units and reconstitute the translations. In neural MT, we are trying to avoid any minimum translation units, any translation units. We come up with a network architecture that reads the input in as original form as possible, and people are now using actually character sequences instead of words, and they produce output in as final form as possible. The only thing is that it has to be practically optimizable, and that's the hard part. But that's like core machine learning. It's not related to machine translation. So this was a talk about machine translation, and you haven't seen any triangle so far. So I think that's a pity. So here's the triangle. It's maybe a different triangle than you thought. It's the semiotic triangle that appeared in the Meaning book by Ogden and Richards. So that's the triangle between the symbol that we see. I'll get to the details in a second. Between the symbol, the referent, and the thought or the reference that's in the head of the speaker. Before we can go into these details, let me talk about the manifold hypothesis. So that's the hypothesis that the deep learning people have. They think and hope for and find evidence for that if you have a sensible representation, then the highly dimensional space has some nice properties, and similar objects or related objects will be close to each other in that highly dimensional space, depending on what the space is designed for. If we put it in like the regular words, the related objects live on the same manifold. Well, in Czech, just to be sure, manifold is varieta. So this, some people need to study the whole master degree to find this. So manifold is varieta, and that's like locally. Now, how is the definition? You would know better. So it's locally. Jo. Je to zkroucený. Yeah, so that was basically the summary. So manifold is a lower dimensional subspace in a higher dimensional space. You can think of a folded paper, halfway folded paper in 3D. So that's the prototypic example of a manifold. And the neural networks are learning space transformations to disentangle the relevant manifolds. So from vision, I've stolen this example. There is a link to these slides, to the slides I stole from later in the representation. So the goal here is to do the face recognition, which is a subtask of object recognition. So we have many pictures of this Joe of his head from many different angles, and we start indeed with the pixel representation. So these pixel representations, these images of the Joe's heads are very different. We would like to be able to distinguish, to separate this Joe manifold, all the representation of Joe's heads in the various positions, from not Joe's, from Sam. These would be all the representations of all the pictures of Sam. And if we are able to like separate these areas in the highly dimensional space with a linear plane, then we can just apply a linear classifier on that, and everything that's above the plane will be Joe, and everything what will be below, then that will be a Sam. The problem in practice is that if we just take the pictures, the pixels in the images, these manifolds of all the Joes and all the Sams will be entangled together. They do not have nice properties. So if we apply a cascade, the cascade of the transformations that you saw in the previous slides, then hopefully you will be able to disentangle them, to tear them apart, to change the coordinate system from X and Y and color to whatever, the head tilt and the distance between eyes and whatever is relevant. It will learn automatically. And then in this other dimensional, I don't have to say higher dimensional, it can be actually lower dimensional space, but in this other dimensional space, in this transform space, the Joe and not Joe will be separate. So that's it. So it's the untangled explicit object information. So now the semiotic triangle again. We have a symbol, a sentence. Danny approached the chair with a yellow bag. And you know that this sentence can correspond to two situations. This is the Danny, that's the lava corpus, a nice corpus of ambiguous sentences equipped with videos and images. Here Sammy is holding the bag. And here in the other understanding, in the other meaning of the sentence, the chair has the bag. And Danny is just approaching that. And then the thought or reference would be the idea that the speaker had in their minds. So if we are like syntacticists, we would draw some trees. If we are semanticists, we would put some lambda formulas here. And I don't have the vectors, but we could put some horrible vectors full of numbers if we already had the representation. So here is another example from or another motivation from vision. And that's the Carlos tutorial on vision. So let me start with vision. This is the poor monkey, and this is the primate non-human brain. The neurologists already think that they know in what parts of the brain are the first neurons that process the visual information coming from the retina, and how these are connected to other parts, and in what area of the brain is there hopefully some like deeper or higher representation of the object. So the poor monkey sits there, and they have little electrodes connected to its brain, and they show it some objects, and they measure the responses in that particular area. So either they measure it in the V4 area, or they measure it in the IT area. I don't know what these are, but there's two different areas in the monkey brain. Yeah. So the idea is that the monkey sees the object, and then through the cascade of calculations or neuron firings, it will actually come to the situation in this IT area where there are features relevant and descriptive of the object, so that just a linear classifier on those will tell you it's a rabbit or it's an eagle. So the space represented by the neuron activations in this area is much more simple with respect to object recognition than the original space of the x and y coordinates in your retina. So what they did, and what's reported in the papers and the tutorial, is that they checked the hypothesis whether automatically evoked spike rates code distributed over non-human primate IT cortex can fully explain human object recognition. In plain words, they were able to interpret the signals captured from the electrodes in the brain of the monkey, and then do the object recognition instead of the monkey. So they connected in the middle of the processing, use the monkey, use its eyes and half of the brain, and then replace the second half with just a linear classifier and identify the object. And they linked it to the human processing vision. So they didn't cut humans; they just cut the monkey, and they assumed that the monkey is similar to the humans. And yeah. So how does this work? I think I'll skip the details again, but in essence, they generated a large set of images. They are artificial, so there is the object you have to recognize, and there is some background, and you can vary it a lot. So they have the 3D model of that object, so they can present the object from whatever angle and whatever scale they want. They can change its color and everything, and they use many images, so they can put it on various backgrounds. Then they check in which settings it is hard and easy for humans to distinguish those objects. So obviously, if you have a red object on the red background, it will be difficult. And if the object is from an atypical angle or strange behavior, again, it will be a difficult task. Sometimes the task will be easy. So then they have an amount of variation. So how much they fiddle the parameters when creating the image, the composed image. And this is what were the objects. So if it was animals, boats, and cars, and here, color-coded is the performance of humans. So, for humans, it is easy to recognize faces with low variance of these generated images. It is difficult to identify boats in highly varying setups, like boats floating upside down in the trees and similar will be difficult for humans. So I don't know exactly whether this was the time needed or the accuracy of recognition and all that. Okay, and then they presented the same set of artificial images to the monkey, and they recorded what the monkey thinks in the early stages, the V4 stage of the brain, and the IT stage of the brain processing. Yeah, and so this is the recording of the monkey thinking. So this is the meaning representation, the intermediate meaning representation in the monkey head, and this is the linear classifier. They just again adds a weight to each of those neurons, and it is trained on a part of the data, on a held out part of the data, to do the prediction of the object instead of the monkey. So that's the process was cut into the middle. You use just half of the head of the monkey, and then the rest is artificial. And it's very simple. So it's just a single layer classifier. And what they find out is that the complexity of the task or the difficulty of the task correlates. The human difficulties correlate with the monkey plus linear classifier correlates. So through this correlation, they can say we really believe that we can understand the neural signals in the monkey head, because our system behaves in a very similar way. It struggles with same examples as the humans struggle. yeah. So, and they even can say when does it appear in the monkey head. It's between 1 and 200 milliseconds after presenting the image. So they can they simply identify when the monkey has the representation of the image that is sufficient to identify objects. It's 100 to 200 milliseconds after that. So yes, that matches. So summary of this vision. Recording aids neural activity and attaching a single layer network to interpret it, and measuring human performance on the same object recognition tasks. We can relate them, and we can support the hypothesis that we know how humans process images. So we can do a similar thing in language understanding. We will record the behavior of a neural MT system because we have all the parameters to access it. We cannot really talk to monkeys and expect monkeys to read and translate, but we can do it with neural systems, and we don't have to cut into monkeys' heads. That's also nice. We can relate it to human behavior, and we can record objective things, reading studies, eye tracking, all that is available, or subjective things, and again, do this on the same language processing task, like difficult sentences, easy sentences, sentences with rare words, sentences with particularly alarming words or boring words. And in this test suite and observing the relation, we can check which of two different NMT models is more human-like in its performance. So if you are familiar with machine learning, this is like a kernelization trick. Instead of directly comparing the neural MT behaviors, if you have two systems or neural MT and the humans, you just check how they perform on a fixed data set, and then if they perform similarly, you assume that they are similar internally. So yeah, okay, let's skip further. So here are the aspects of meaning of expressions of natural languages that I was able to come up with, but I would like your comments in this at this point. So when trying to find out what is the meaning, what will be meaning for me, I think the most plausible answer was that meaning is a coarsening of whatever message you have. So in pictures, the task is called semantic segmentation of pictures. So here is the example. So we have an input image, and you can ask an automatic segmenter to segment it into object, into a class. You can segment the picture into areas and color code them so that each color corresponds to a different class of people, like a different class with the labeled people. So this distinguishes people and non-people. So these are like people areas and non-people areas. You can do also instances of objects. You will have the class of no people, and you will have a class of one person, another person. So you will train the network to do the separation. And you can also link it with some description, and then the description could be like, show me the people in the blue coat, the people in blue coat, and it will understand the expression, and it will identify the area in the picture that corresponds to people in blue coat with this. So that's like the meaning of the picture, given some further constraints, is this coarsening of that picture. Instead of the 256 color codes that you have here for every pixel, you have just 2 or 5 colors, and you have much larger areas than individual pixels. So that's like what a meaning of a picture could be. In programs, the meaning is what the program gives you for all the various inputs. But remember, we're at math faculty, so we know that this is undecidable to check whether two programs produce the same output. But in practice, for many reasonably small programs and the reasonably small outputs, we could check whether they produce the same output. So in practice, we do not need to worry about the undecidability too much, hopefully. So I don't know what the meaning would be in computational linguistics. Some reference to the real world. Some speaker's intention, like I would like you to bring me coffee or whatever. Yeah. So that's one aspect. So meaning is some coarsening. Then we as computational linguists and speakers of natural languages, we know that meaning can be shifted and modified in various ways. So this is like you've seen the king being modified by subtracting the gender of man and adding so that's like a modification of the meaning, and we would like to get to the expression that corresponds to the modified meaning. Meanings can be compared, so there can be like oppositions, and meaning is generally compositional. This is a hard one. So from a small expression and from more small expressions, you are composing a larger expression, and it has a meaning which is somehow derived. So you have hopefully attended some of the semantics and logics classes. So that transparent intentional logic is something that I would highly recommend in this respect. So the linguistic meaning that's treated at this particular department is, as far as I've understood, the structure of the expressions, such as morphology and syntax, without really going into the semantics. So that's why lexical semantics is neglected in this department as well, because we're mainly concerned about the structure of sentences. Please correct me if I'm terribly wrong. So, and then there are aspects of meaning that I've wrapped under the label pragmatics, and I don't know whether this was right or wrong as well. Some named entities and numbers appearing in those things. These things terribly affect the meaning of the sentence. If you are doing machine translation and the numbers get screwed up, you will say that the meaning of the sentence got distorted in some way. So they are part of the meaning, but I don't know where to put them directly. Yeah. So there's another aspect that we really know about. Expressions are ambiguous and meanings are vague. Perhaps even the speaker doesn't know quite for sure what he's thinking about. And there is this aspect of continuousness of meanings that arises, especially in the highly dimensional vector spaces that we have seen previously. And there is this aspect of statefulness, and I'll have a slide on that. So the compositionality of the meaning, let's skip it. The statefulness. So if we have like a stateful representation of meaning, it will encode the state of the mind after having read this sentence and having produced the output so far. So that's like neural empty stopped in the middle, and then the deep representation the neural empty has could be directly read off and related to some human meaning. So it corresponds to models with attention. That's what I've skipped in my presentation. And by the way, this would be necessary to be able to interpret humor, because there is always some flip. When you are telling a joke, at the beginning you have some understanding, and at the end you have a different understanding. So you have to have the stateful representation of the meaning in order to capture that. And the stateless meaning, stateless representation of meanings, then you have the large space, and these points in the space can correspond either to expressions, but that doesn't really fit. Then the ambiguity representation is unclear, or the points can correspond to meanings, and that's like the neural empty models without attention. That's what I've talked mainly about. That you take the input sentence and encode it into fixed vector of fixed length, and then you inspect it in various ways. Perhaps you attach the decoder that produces the sentence from that. So, is sentence meaning continuous? So that's a question that I've asked myself, and maybe you know the answer from the top of your head, but I'm not sure. So we know that there are many paraphrases of a sentence. So for this English sentence, we have 71,000 possible Czech translations. They are generated by humans. Some of you might have worked with this data set, and I've heard complaints about the data set, but generally most of the translations are all right. Let's skip that for now. For English, the same was observed. Many possible variations of a sentence. So the questions that I have now is, are all the paraphrases close in the embedding space, in the space of sentence embeddings? And how entangled are the manifolds of different sentences? So hopefully the space would actually put all the paraphrases close to each other and all the different sentences with different meanings further away. So I'm working on this because Holger Schwenk is one of the like big names behind neural MT, and he has a model that produces insensible embeddings, sentence embeddings. He's actually doing machine translation by search. So he just takes the input sentence, collapses it into a vector, and then searches for similar vectors in that area. And there, because he has encoded all the UN languages there, he can pick whether he would like to like generate the Arabic or the Chinese or the English version from that area, and that's what he does. And if he finds sentences that are translations or close translations to what he fed in. Yeah. Okay. So that's one thing. Another thing is the ambiguity. Sentence level embeddings. Maybe let's skip this for the sake of time. Simply, the idea is that the decoder in the encoder-decoder architecture is the thing that deterministically maps from the hidden meaning, from the meaning representation to the expression. So we can ask how many meanings and which meanings correspond to this expression. So we need to like reverse the decoder. This is about so far failing experiment, but about reversing the decoder instead of encoder. So maybe if someone wants to ask about this. Another area of experiments is that examining the continuous space of sentences. I'm with Chris Cliston-Birch and people at Mechanical Turk. I'm now trying to generate continuous like a sequence of sentence examples so that they are continuous. And then I would like to check whether I see the same continuousness in the embedding space. So I propose like directions of exploration. I generate pairs of sentences for each of the directions, and I collect and I ask people, tell me something in between these two sentences. And then I will validate the relations and create the partially ordered set of the relations. So here are examples. So it could be like politeness coming next, verity, how much does the speaker believe in the message, modality, how much is the speaker willing to do something or able to do something. Then some generic numerals counting or scalar adjectives, negation, how complex is the sentence, say the sentence in a simpler form. How specific it is. So geese fly, or geese migrate south, or the Canadian geese flew over the pond, blah, 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 and so on. So contextual boundedness. Hey all, it's a nice day, ain't it? Well, I'm not able to speak that low class English. And then the nice variant would be greetings, lovely weather are we having. So these are all sentence variations. They should live close to each other in sensible sentence meaning representations. So what we are doing, we are asking people to give us pairs of extremes. So for politeness, these are pairs that random Americans gave us. Can you please give me a minute? Could you leave me alone? Another pair would be close the door, close the damn door, man. Or can you help me find something, and I need you to help me get something. So these are pairs, and then in the next stage, for each pair, we ask people, tell me a sentence in between, and we give these two inputs. Can you help me find something? I need you to help me get something. And then these are the candidates that people came up with. So would you help me look, find this for me, help me find something, please help me find something, will you help me, your assistant in finding something is required. And we can then ask another round of annotators to order them, to put them in a partially ordered set, and then each of those sentences through an encoder can be mapped to this highly dimensional vector space. And the hope is that the structure that people will see among these candidates will be identified as a structure in the highly dimensional vector space. So that's like finding the manifolds of similar sentences or sentences related in a particular way along the various dimensions. Another example, let's skip that, and then another example. Yeah, so I've started with saying that the neural MT is the black box that you feed in the sentence, and it gives you the sentence, and surprisingly it outperforms everybody else. And then, because this is actually true, I've moved to a harder target. and the harder target is understanding how people understand. And in that respect, the neural networks are much less opaque than a human brain. So the idea is to use the networks as a proxy to the human brain, and use various techniques of neural network exploration to test the hypothesis about the how meaning is processed in our own heads. And I've listed some techniques that are already available for exploring neural networks. Let me skip that for the sake of time. But we have seen some. One of those was attaching a neural network to the hidden representation, attaching a single layer as a classifier. And there are papers, for example, it is possible to check or to find out the subject-verb agreement for some neural network architecture. And it's possible to do part-of-speech taggings based on the sentence representation that the neural MT has created. So doing similar things, we can see whether the hidden representation of the sentence knows about politeness, knows about the parts of speech, knows about syntax. So that's one of the possible things. Okay, so here's the summary. The deep learning should be afraid of computational linguistics because it's all the great tools they have that we can now use to do our subject of study, to examine how people learn and use language and understand language. So to summarize the talk, neural MT has reached, and sometimes it can surpass human translation quality, but still catastrophic errors do occur. I've listed only some of the network architectures and not the most recent ones. They appear every half a year at least. So there is big progress still coming. So back to the original question, in 2 years from now, machine translation as a task alone will not be interesting. It will be interesting as a proxy to understanding how people understand, but from the practical point of view, it will be solved, I'm quite sure. As a side effect, the networks learn some continuous representations, and we have seen that in the vision, which is an object recognition, which is arguably much easier than understanding of natural language sentences, it was possible to gain insight by comparing the computer and human or primate vision. So we have plenty of data, and we can easily obtain other data. We can create neural MT systems that process the data. So let's train the natural language understanding system, and let's dissect them instead of dissecting monkeys or people. Yeah. So that's it.
Thank you very much for your very interesting talk. I'm afraid we won't have too much time for discussion, but still we can start discussion and maybe continue in between two or a group of people in the discussion. So, the first questions.
Many speculative.
Okay, before I leave, I'm sorry, I have to leave in a couple of minutes, and he knows that. My question is very naive. I think that, well, there is a scientific, I hope, scientific discipline of theory of translation. And in the last part of your talk, I would like to see what people from working in the theory of translation, whether they have something to say or not.
Yeah. So would I. I have contacts to some of them, and I'll definitely try to use them and revive them and to find out, because yes, by asking the questions or proposing the topics that I proposed in my talk, I'm moving away from just machine translation, and I think I have to do it, because otherwise, indeed, it will be solved in 2 years from now. So I'm broadening my scope, and when doing that, I really need to study so many different disciplines, and translation studies will be definitely part of that as well. Yeah, thank you. Yeah. So
Tens of questions.
there was too much and too confusing content.
Just a remark about translation studies actually reminded me of a talk that we've heard in Bratislava last week about there was someone reporting on problems of translations of legal documents. And it was sort of like domain adaptation, but a hard one, because there are ordinary words that get fixed meanings, sometimes quite shifted from what a normal person would think about it. And not only that, but quite often, even if you are in one particular subset of law, the definition is quite different from the same word like in criminal law versus economic, business relations, and so on. So, don't you think that there will be, if those people ever trust machine translation enough to use it as a tool, isn't there still quite a long time to adapt the tools to that?
Yeah, that's true. That's definitely true. So the legal domain, I've tried Google Translate on some English to check translation. No, check to English translation, which is supposed to be easier, of a sublease agreement. And it translates sentence by sentence. And the word nájemkyně can be translated as lessee, tenant, in some cases, and that was the case, even landlord and sublease or something like that. Yeah. So there are at least 4 different English terms that can be used. And it used all of them as a rainbow in the translation. And there were 2 parties, and for each of those 2 parties, it was possible to use all of these 4 terms. So the resulting document was totally incomprehensible because all the parties were totally mixed. So yes, there is still a lot of research to be done in MT alone. There are no shared tasks in this area yet. We can start them as long as the shared tasks remain broad. And well, the WMT is moving towards document level translation, but I think there is surprisingly little coherence necessary to translate news. That's what we are translating at the moment. If you translate news sentence by sentence, you are not making too many errors. If you translate legal documents sentence by sentence, you are much more likely to cause serious errors. So if the WMT remains with the news, then I think it will be really solved. So we should propose move to legal documents or other special domains, and then there will be a lot of work to do. But then the problem is that the field becomes fragmented. So there will be different competitions in different subtasks, and like the traversing across these would be difficult unless we make a giant task of all the domains at hand. So yes, there is also a clear way to go. At the same time, I'm really curious about understanding more, and as I put it, neural networks seemed to me very opaque. So I chose a goal that is more opaque than they are, and therefore I can use them as a proxy and an easy to explore object of my research. So.
Well, so I still have time to add one historical remark. Those who have been staying with us for 30 years, I don't know how many of you belong to that group, may remember Zdeněk Kiršner, who was the first here in the beginning of the 70s to work in machine translation. And you may remember one of his examples, and I was reminded by your first example with negation, because he gave the system English sentence, "This machine is very intelligent," just wanting to say how the machine is nice. And the translation he got in Czech was "Tento stroj není inteligentní." he explained to me why this happened, but it was certainly without statistics and without neural networks. But it's one historical example of how sentences can be misleadingly translated. Yeah.
Thanks for a really interesting talk. Maybe I have a couple of questions. When you're saying that machine translation is getting close to being solved given the current evaluation metrics, maybe we're using the wrong metrics then? Maybe the metrics should be redefined and we should pay more attention to the catastrophic errors, because these are the errors that are showing that actually the systems are not understanding the sentences as such. They're just kind of doing a sophisticated translation which works in most of the cases, but if there are catastrophic errors, that means that there's no actual understanding going on.
You're totally right. So the current success of neural MT says more about the simplicity of the translation as a task than of our capability of mimicking humans. So the phrase-based MT was already surprisingly successful, and that means that most of the translators can most of the time just do copy and pasting. It got obviously, if you did this phrase-based copy-pasting, then you were bound to produce sentences that are not quite grammatical. So the neural MT is the device that makes the copy-pasting flexible somewhat, but still you do not need to understand. The systems are not understanding and they are making serious errors. And by adding these the ideas from understanding and checking whether a system has some representation that behaves similarly as humans behave with respect to meaning, I'm hoping to identify architectures that are better at understanding of the sentences. So that's like my planned research direction. To the metrics issue, the problem is that even humans. So this the final evaluation in WMT is done by humans. So it's not limited to automatic metrics. Still, there has been a long debate, and we have contributed to that actively, how to do the evaluation, and it's hard. If you're coming from the translation studies area, then you probably know that two translators will never agree on what is a better translation. So how to really measure that, people are actively working on this. So every year it's not only new systems, but it's also a slightly modified evaluation metric. So yeah.
Thanks. And a second question, my knowledge of neural networks is very superficial, but I know there have been arguments against actually, well, let's say, ecological validity of the model, or in other words, that human learning, there are important differences in between how neural networks work and how human learning works. So if you could say a little bit about that, how you're these differences, and since you're actually considering or already conducting research on neural networks, that you want to see how these could impact our knowledge of how human learning works. So if you could elaborate on that.
I have no knowledge about that yet. This is something that I definitely need to learn about. I know that the name neural networks is only like to vaguely resemble the neurons. It's just matrix multiplication. It's nothing natural as we have in our heads. It is a model of what we have in our heads. I'm not aware of the differences. Like I'm aware that there are some, or maybe many, as you say, but I don't know which they are and how harmful are they. As long as we can build a device that behaves similarly, that passes the Turing test, we are fine. It's a good model of what we have in our heads. So I would bother about the differences only if we like keep failing, and the failing means not to make a system that is better than humans in a task, but to make a system that makes the same type of errors, that is indistinguishable from humans in terms of error making.
That's one thing, because what I've read about neural networks is that you can fairly easily engineer examples that will totally confuse them, which would not confuse humans, right?
Yeah, exactly.
And that the learning works in a way that you need, in general, billions of training examples in order to achieve, a good performance, whereas humans, we don't encounter billions of examples of cars before being actually able to recognize a car, right?
And
So-
never mix it with a giraffe because
So,
the
yeah,
example
right.
was engineered that way.
So the type of generalization that we do seems to be different in
Yeah.
quality than from what the...
This, the adversarial examples that you are mentioning, they are exactly an evidence that the neural networks are not understanding. So I hope that by training them at like a small scale and large scale at the same time, you can make them resilient to these types of examples. So if it appears as a car even reduced to 4 by 4 pixels, and if it appears as a car in this full resolution, then hopefully you have not been tricked. That's the idea. But yeah, the research is still to be done there.
Okay, thanks. Good luck.
Well, thank you very much. I'm afraid we have to stop the public discussion, but I think that private discussions will just go on and on and on, because the topic is very interesting from many points of view, and I have made some notes as well. So that's all for today, and next week we will welcome Professor Karlik from Brno. So in a way we will shift our attention to the form of expressions rather than to the function, as was your talk. So thank you very much.